Hi everyone, welcome to Machine Learning from Data. This is lecture 14. And in this lecture, we are discussing something that's known as learning principles. So in essence, we will look at three learning principles. The first one of them is the Occams Razor. Second is sampling bias, and then finally data snooping. So the first one, this Occam's Razor, we will spend some time discussing this, and that is because it's related to the choice of your model. Whatever we've talked about models, how to select, and other things that are related to model complexity and all of that. So that's Occam's Razor. The other two learning principles, sampling bias and data snooping, are also very important principles, but they are related to data in general. Sampling bias, for example, establishes an important principle about how to obtain data. And data snooping, I think we have talked a little bit about it, and that relates to handling the data. Right? So, a very good understanding of these three principles is essential for a machine learning practitioner, and basically there's nothing new here. We have talked about these, we have looked at these, and now is the time to put things in perspective, to really understand what's going on where, and how to deal with different issues that come up when we solve a machine learning problem. So that's the goal for today. A quick recap, just like we do every time. So last time we talked about validation and cross validation, right? So two techniques, and then finally using them for model selection. Basically, the idea behind validation was that we are directly trying to estimate E out. And to do that, what we did was we were splitting the data set into validation set and then a training set. And then based on that, we were using something that's known as eval of G, this thing, to estimate my E out, right? And so then we found out that there was the size of K, the number of data points that or the size of the data set rather, that we allocated to our validation set that impacted our quality of the predictions that we were making. So if K is too large, then my G minus, which was my final hypothesis, the deficient hypothesis, was less reliable, right? And if it was too small, then the link between E out of G and then this eval was somewhat questionable. So in order to resolve that, the dilemma of K, we use something that's known as cross-validation here. And so cross-validation makes things easier for us because we just take K equals 1, but K equals 1 means that the validation, we are just leaving 1 point out, and then we are basically coming up with these hypotheses, and then finally the overall result is dependent on the average over all those possibilities. So we get E of CV, which is nothing but the cross-validation error, and it's a good estimate of E out. And then basically what we were doing were we were training on n minus 1 point, so we were extracting the most information from our data set. One of the most important usage of validation and cross-validation in particular was model selection, because we can actually run these like different models as like black boxes and come up with these final hypotheses, and the selection criteria would be based on some of the techniques that we used in validation and cross-validation. Another, I think that I forgot to mention, another application was to get the regularization parameter. So basically regularization parameter lambda selection. That's another application of validation and cross-validation. Okay, so having recapped what we talked about in the last lecture, let's begin with the very first principle of learning, which is the Occam's Razor. So what is this Occam's Razor talking about? Basically, it's talking about, as it's given here, an explanation of the data to make it as simple as possible, but no simpler. So why is the word razor coming in? That's because we must use a razor to trim it down, right? So this is like from the 14th century, William of Ockham, who said razor means to trim down, and like the explanation to the bare minimum that is consistent with the data. So data is the essential part of any problem that we're trying to solve, and it must be explainable in the most simplest form. So that's what the fundamental principle of Occam's razor is telling us. Okay, so what does that actually tell us? Well, simpler is better, which means the simplest model that fits the data is also the most plausible. What does that mean in the context of learning? Well, the penalty for model complexity, right, which we introduced in one of the earlier lectures, is essentially nothing but something that's representing this Occam's razor. Well, how is that? That's because if, let's say, in like a machine learning problem in general, I'm getting some En of G equals 0, now we know that we're not done there, right? Because this hypothesis, although is consistent with the data, right, um, it has to be the most plausible explanation as well, which means we need to have a good E out as well, right? So basically what I'm saying is data is the essential component of my learning problem, and we should throw away any information that's making my model complex. For example, from the perspective of the VC theory, we know what happens when the complexity of the hypotheses um, becomes big. So we would like, so basically something happens to the VC dimension, and so we would like it to be as small as possible. We like this VC dimension to be as small as possible. And so that's why we are saying that the simplest model that fits the data is also the most plausible one, right? So that's the idea behind the Occams Razor. Now, according to this principle, we should choose a model as simple as we can think of, and it fits the data. That's what the principle is telling us. And it is intuitive as well, given all the information that we have about machine learning now. Now, but when we apply like this thing, okay, this is an intuition, or maybe this is based on some facts, and now we're saying that simpler is better. So now the questions, two basic questions that come to our mind are, what is the meaning of simpler? What is this simpler, right? That's the first question that comes to our mind. And then the second question that comes to our mind is, how do we know that simple is better? So let's answer like the first question one, and let me write down question two as well. So question one is what, maybe question one is, what is simpler? What does simpler mean, right? And question two that we'll try to answer today is, how do we know, like, why, or maybe how do we know that simpler is better? That's a better way of putting it. How do we know, like, what's the basis for this, that simpler is better? All right. So let's begin answering the very first question, that why, first of all, what is simpler, and then come to why is, like, how do we know that simpler is better? So what is simpler? Now, we have two sort of definitions for simple, and we've come across both of them until now. So the first one is simple hypotheses. We've looked at that when we were doing regularization. We've also looked at when we were talking about some order polynomials, right? So then in that situation, we were talking about a low order polynomial, right? So there are essentially two distinct approaches to defining this notion of complexity, right? And then, for example, in the VC dimension in chapter 2, a measure of complexity was based on the hypothesis set as a whole, right? We came across that a lot. And so it was based on some like collection of objects, right? And then in chapter 4, as I said, we came across a simple hypothesis when we were using regularization term for the augmented error. And that is also a measure of complexity, because in that case, the complexity of an individual object, which is my simple hypothesis, was taken into account. So when we were talking about like simple hypothesis sets, we said the VC dimension should be small, or maybe the number of hypotheses in that set are less. Low entropy set. Low entropy is also a measure of like complexity based on a family of objects. So like minimum description required to describe certain objects. So that's all of that comes in like simple hypotheses, right? And then in terms of like a single hypothesis, we came across like a simple, like a low order polynomial is simple, right? And so we basically what's saying is that you need very few parameters to kind of describe it. So in general, a hypothesis set with simple hypotheses, either way, must be small. So that's what the idea of a simple hypothesis is. Because in general, as I said, each individual object in a family, like let's say there's a family of objects, right? And so why do we always say, whether in the case of a simple hypothesis or a simple hypothesis set, you must have noticed we say that when the number of objects is less, we say that this is like less complex. And yes, even in learning, the same idea has been taken forward. And so we, like in case of a simple hypothesis, we say that when we have less number of terms, so you need less description for that. And that's why it's simple. In this case, you have fewer choices. So in both cases, like fewer is related to a simple hypothesis. So simple must be small. So that's the fundamental idea. That's what simple means when we say simple. So it could be either according to the VC theory, it could be according to us what we did with regularization. All of that holds, right? So simple means small. Okay, so having established that, now we want to go ahead and see why is simpler better. Okay, why is simpler better? One intuition about it is that, like with a simpler model, when you fit the data and then you find that it fits well, and that is a reason for surprise for you because you least expected it, right? So when you're like more surprised when you fit the data, when something unlikely happens, it is very significant when it happens. So that's the idea, that's like that this is why simpler is better. That's like another way of putting it is like simpler has a better chance of being right, right? So the if a complex explanation of the data performs better, we will take it usually, right? But then you don't expect it to fail. But then with a simpler model, you least expected that it will give you the best result, but it does. So that's why simpler is better. And of course, we are going to dig deeper into it, looking at an experiment and see why we are saying this. Like, what do you mean by it? We'll get surprised when we see that the data fits. Okay, so let's look at this nice scientific experiment. And this is taken from the textbook. This is example, I think, 5.1 in the in chapter 5. So this is about like a physical theory, and it's known that in theory, like apart from certain constants, the resistivity that's given here, it's like just think about it as a variable, like rho has a linear dependence on temperature T. Maybe you've seen it in some of the physics classes. Now, in order to verify this theory, so this is a theory that like resistivity depends is linear to temperature in certain ways, and so we have to verify it. So we'll collect data. So the experiment is about three scientists collecting data, and then basically the question we're trying to answer here is that who provides the most evidence for the hypotheses that rho is indeed linear in T, right? So that's the goal here. So as you can see, if we just like look at the data and see the linearity here. So if you look at scientist number 2, right? I can just like by looking at it say that it's like very convincing. It looks like extremely convincing to me because it is indeed, you know, proving that theory that rho is linearly related to T. Now, in contrast, if we look at scientist number 3, right? So as you can see, this doesn't like, it's not completely linear, and if we try to kind of fit something here, it will be non-linear, as you can see. So that I can say there is some evidence, and if we allow some slack, if we allow some error, some measurement error, then maybe we can take this as something that's uh, kind of, proving the theory to a certain extent. So maybe this was like the most convincing, and then this was like a little bit convincing, but not quite. Now, if like the measurements are exact, right, then scientist 3, we will say here, has managed to falsify the theory, and like because this is saying that this is not linear in some ways, right? So falsify meaning that we like there is evidence to prove that this might not be the case, right? So yeah, there is some evidence to show that there is some falsification. Okay, what about scientist 1? We didn't talk anything about the scientist 1. Now scientist 1 has just given 2 measurements, right? And the whole point here was to show whether rho is linear in T or not, right? And so scientist 1, if you look at it, has given us no evidence whatsoever of the hypotheses. What does that mean? Well, you can always join 2 data points with a line, right? I can like have any 2 points and I can always join them. That's a basic like geometry or like some elementary level math that tells us that. So like I could have fitted not just with a line, but any other curve here, any complex curve, and that would have like again proven that theory, right? So basically, in case of scientist 1, although the scientist 1, has not falsified this theory, but they have like uh, not provided any evidence whatsoever, like whether this is right or wrong. Okay, so this experiment kind of gives us an idea of, and we come to something that's known as a fundamental axiom in learning theory, and that's stated here. This is known as the axiom of non-falsifiability. So that, and this is like fundamental to machine learning. This is important for every experiment, every data that we have, whatever we are working with it, right? So basically what it says is if an experiment has no chance of falsifying a hypothesis, which was this scientist's case, then the result of that experiment provides no evidence one way or the other for the hypothesis. For example, if you have a hypothesis and you run an experiment to test that hypothesis, then it must be the case that your experiment has the chance to falsify your hypotheses in order for your experiment to be worth anything. This is what we are trying to say here. For example, like for scientist 2 here, in this case, there is some way that this can be falsified, right? So if I found like 3 points that were not linear, then there was a way of like falsifying that there is no linearity or a linear relationship between resistivity and hypotheses. But scientist 1, no way you can falsify a linear hypothesis with 2 points, right? So basically what this is saying is there is no point doing this experiment. We cannot say if the hypothesis is right or wrong because your experiment provides no evidence. And that's the axiom of non-falsifiability. The axiom asserts, as the book also says, that the data should have some chance of falsifying a hypothesis if we are to conclude that it can provide the evidence for the hypothesis. So that kind of like scientist 1 has demonstrated what exactly that means. So how does what is the applicability of falsification in machine learning? Let's look at that.